Hello. In the last lecture, we are discussing about the equation of Cron's primitive machine model, and we have derived the equation for the voltage in terms of the resistive drop, the inductive drop, and the speed EMF. Now, this is the equation that we are discussing in the last class, that V is equal to Ri plus LPI plus omega R GI. Now, if we pre-multiply this equation with I transpose, what you obtain is I transpose R I plus I transpose L P I plus omega R I transpose G I, this equation. Now, we have already seen that the first term, term 1, represent the losses of the system. This is basically the first term, term 1, R transpose R I, term 1 represent the system loss, I square R loss, and the term 2 represents the power associated with the magnetic field, or the power stored in the magnetic field. And the third term, term 3, which is omega R I transpose G I, is the mechanical power output. This is what we are discussing in the last lecture, that the second term is the power associated with the magnetic field, the third term is the mechanical output of the system. Now, to recapitulate, we have already seen that V is equal to R I plus L P I plus omega R G I. Now, this equation is a voltage equation. If we pre-multiply this with I transpose, we get the following equation: I transpose R I plus I transpose L P I plus omega R I transpose G I. Now, this equation is interesting because the first part is the electrical input. The second part, which is I transpose R I, represents the system loss. This basically I square R loss of the system. We know that the Cron primitive machine model has 4 windings, one winding in the D axis stator, one winding in the D axis rotor, one winding in the Q axis stator, and one winding in the Q axis rotor. And I transpose R I, this term represent the system losses, I square R loss of the machine. And this term is associated with the inductance L, and we know this L matrix, L is a matrix we have seen in the last lecture, which has got the self inductance and also the mutual inductances. And this equation, or this particular term, that is I transpose L P I, is the power stored in the magnetic field. So, we can say here this is the power stored in magnetic field. This is not converted to the mechanical power. This is basically the power stored in the magnetic field, which is the self inductance and the mutual inductances, and this power is not converted to the mechanical output. What we have here, this the third term is the mechanical output. So, we can say that this is the mechanical power output. And if we find out the torque is P make the mechanical output by the mechanical speed omega r m, and that's equal to, this is your P mechanical. So I can say here omega r I transpose G I by omega r m, and that's equal to omega r I transpose G I by omega r by P by 2, and that's equal to P by 2 I transpose G I. This is the expression for the torque. This I is a vector. I has more than one elements here. So this is the expression for the torque of a Cron primitive machine. This is what we have discussed in the last lecture. Now in this lecture, we will try to discuss how this Cron primitive machine model can be used to simulate a DC machine. First of all, we will simulate a separately excited DC machine. Let us see. Modeling of separately excited DC machine. Now what we have here, if you see a separately excited DC machine, we have the armature, and we have the field winding. And these are the armature terminals. We can apply some armature voltage here, and this is the field winding, and this armature winding can be replaced by pseudo stationary winding, as we have already seen that this is the two brushes and this is the pseudo stationary winding. So here what we have only two windings, one in the D axis, this is our D axis, and this is the Q axis. So we have one winding in the D axis stator and one winding in the Q axis rotor. This is basically the rotor here, and the field is on the stator. So we have the stator in this case. Now this we can call to be the DS winding, and this we can call to be the QR winding. So we can write down the equation here. We have just two windings here, so we don't have to write a 4×4 matrix equation. We have to just write here a 2×2 matrix equation because we have only two windings in this case. Other windings are non-existent. So we can write down the equation like this: VDS and VDR. This is the rotor and this is the stator. That's equal to, we have to write down the impedance matrix, and the currents are IDS and IDR. All right. So we can write down the equation here that VDS equal to RDS plus LDSP, and this is 0, and then we have RDR plus LDRP, and the rotor, as we have already seen that in rotor we have statically induced EMF as well as the rotational induced EMF, because this is rotating in the clockwise direction at the speed of omega r. So the rotor will have rotationally induced EMF as well. So RDR is the resistive drop, LDRP is the inductive drop or statically induced EMF, and we have omega r MD here. This is the rotationally induced EMF. Okay, there is small change here. This is the Q axis. So we have in this case VQR, and this is IQR, and this is RQR plus LQRP. So, this is the resistive drop, the statically induced EMF and the rotational induced EMF in the q axis rotor. Now, of course, we have already said here that we do not have any q axis stator current and we do not have any d axis rotor current. So, these two variables are 0. So, we have a 2 by 2 matrix here and we have to model the DC motor using this 2 by 2 matrix. So, in this case we can find out what is this G matrix. G matrix is the matrix associated with the speed, that is omega r. So, we can write down this G matrix. This G matrix would be 0 and 0 here, and this is MD and 0. This is the G matrix. It is a 2 by 2 matrix associated with the speed, that is omega r. And we can find out the torque equation in this case, that as per the Cron's primitive machine equation, we can say that TE is equal to P by 2 I transpose G and I. Now, here we can say here that the torque equation is as follows: P by 2, what is I transpose? I transpose is IDS IQR. This will be a row matrix. I is a column matrix, and if you transpose it, it will be a row matrix. And then what is the G? This is the G matrix, and then we will post multiply with I. This is what we have. And if we do this MD is a mutual inductance between the stator d axis and the rotor d axis. This is actually MD. And LDS is the self inductance of the stator. LDR, LQR is the self inductance of the rotor. So, these are the various inductances here. And similarly, the resistance of the stator winding is RDS, and the resistance of the rotor q axis winding is RQR. So, these are the various parameters of the machine which are given here. Okay? And then if you simplify this torque equation, we will get the following expression. Now, TE is equal to P by 2 MD IQR IDS and IQR. Now, this we can simplify this as P by 2 MD IQR into IDS. So, this is the expression of the torque of a separately excited DC motor. The field is separately excited, and in this case you can see that IQR, what is IQR? IQR is the current in the rotor winding. So, IQR is same as armature current. So, if you have, this is your armature current, I can say this is your IA. IA is same as IQR because this is flowing through this winding, okay, and this is my IDS and this is same as the field current. So, IDS is same as the field current and IQR is same as the armature current. So, we can replace this IQR by IA is armature current and IDS by IF is the field current. So, we can say that PE is equal to P by 2 into MD into IA into IF. So, this is the torque equation of a separately excited DC motor. So, we have the voltage equation. In this case, this is the voltage equation and we have the torque equation, and we can find out the speed from the torque. How do we find the speed from the torque? this is our torque equation. So we can write down the electromechanical equation to find out the speed. Now that's equal to J d omega r by dt. Now omega r is the electrical speed. So if you want to find out the torque, this has to be the mechanical speed, omega r m, and this J d omega r m by dt is the inertial torque. J is the moment of inertia and d omega r m by dt is the angular acceleration of the rotor, the mechanical angular acceleration of the rotor. We can also have the viscous friction, that is B omega r m. Again omega r m is the mechanical speed and B is the coefficient of viscous friction. Of course, you can also have the load torque TL. So this equation, if we solve this equation, maybe numerically we can get the expression for omega r m. Omega r m is the mechanical speed. Now we can also simplify that. If you express this omega r m in terms of omega r, we can divide by p by 2. So J by p by 2 into d omega r by dt plus B by p by 2 into omega r plus TL. P by 2 is the pole pair. P is the number of pole of the machine and p by 2 is the pole pair. Now this is a first order differential equation we can solve for omega r. So this actually we have the model of the DC machine which has been obtained from the Cron primitive machine theory, and we can find out the currents, find out the torque and then find out the speed. Now let's take little complex problem. Say for example, if you simulate a separately excited DC machine, this is, we have already done the separately excited DC machine. We can now go for a little complex problem, that is series DC machine. In series DC machine, what we have the rotor. The rotor is the armature, and then we have the field winding, and they are series connected. Let me just make the connection here. Now this is the stator, D axis stator, we have this voltage as VDS. This is the rotor winding, we only have Q axis rotor winding, and this voltage will have VQR, and the current is flowing in this particular direction, is returning back to the supply in this particular fashion. So when we go for series DC machine, it is little complex problem, so we cannot solve it directly. So we have to take the help of what is called a linear transformation. So we will be discussing about a linear transformation in electric machines. So we will be discussing about linear transformation in electric machine. Now what is the meaning of linear transformation? Linear transformation is a transformation which transforms the actual variable to the primitive variable without any nonlinear term. Nonlinear term, we mean there should not be a product of two variables, there should not be a square of a variable. Okay? Say how we can tackle this particular problem. Now this series DC machine have been connected like this. The armature is in series with the field winding, and we can write down this equation that IDS here, Now we have one stator and one rotor. This is our IDS, D axis stator winding, and this one is IDR. So we can say that IDS equal to IT. Now IT is the terminal current or the machine current, all right. And similarly I can say that IQR is also equal to IT, because the field current is same as armature current. So IDS is the field current and IQR is the armature current, and both of them are same. So we can say that IDS equal to IT and IQR also equal to IT. IT is the machine current that is coming from the supply. Okay. So we can write down this in a matrix form. So we can say that IDS and IQR is a matrix that is equal to, I will have another matrix, it is a column matrix, 1 1 into IT. IT is just a single variable, all right. So this is a interesting equation which relates the actual variable with the primitive variable. Now this variable is the actual variable. I can say that this is the actual variable. Now this variable is the primitive machine variable. So I can say that this is the primitive variable. And this matrix 1 1 is called the connecting matrix. So I can call this to be the matrix C, and C is called the connecting matrix. So you know that what we are trying to do, we are relating the actual variable with the primitive variable by a linear transformation. That is the meaning of linear transformation. And this 1 1 is not a nonlinear transformation, it is a linear transformation which relates the actual variable with the primitive variables. Now this is about the current. What about the voltage? Now let us see the voltage here. Now if you see in this case, my terminal variable is Vt, this is my Vt. If I write down the Kirchhoff's voltage law, I can say that Vt is equal to Vds plus Vdr. This is a simple equation which can be written in a straightforward fashion from the circuit equation, all right. So I can rewrite this in a matrix form. Now if I rewrite this in a matrix form, I will have the following expression. Vt is actual variable, that is equal to Vds plus Vqr. That is what we have written in the previous thing, and that is equal to the transpose of this matrix So this is the equation once again, and that is equal to, I can say here, the transpose of the C matrix into VDS and VQR. So I can say here that V actual is equal to C transpose into V primitive. This is my V primitive, and Vt is my V actual. So I have two sets of equation, that we have I primitive is equal to C I actual, and I have C transpose V primitive is equal to V actual. So I have two equation, and the actual variables are related to the primitive variables by linear transformation, that is C. Okay. Now you know that the objective of linear transformation is to take help of Cron primitive machine model and get back the variables in the actual variable form. because the primitive variables like IDS, IQS, IDR, IQR, or VDS, VQS, VDR, and VQR, these are the variables of the primitive machine. They are hypothetical variables. They are not the real variables. The real variables could be something different from the hypothetical variables. So if you have the transformation matrix, that is C, you can write down the equation of a primitive machine which is from the Cron primitive machine model, and using the linear transformation you can get back the variables in the actual machine variables. Okay. Now in this case it is a series motor and the machine variables are IT and VT. These are the actual variables, VT and IT. So we have to find out the torque and the voltage equation in terms of the actual variables. So this is what we have here, and we know that V primitive is equal to Z primitive into I primitive. So this is basically the voltage equation, and Z primitive is the impedance matrix of the primitive machine, that is the Cron primitive machine, and I is the primitive current of the primitive machine. Now I can pre-multiply this equation by C transpose. So I have the C transpose here, and I primitive can be written like this, that C into I actual So this equation will lead to a different result, like C transpose into V primitive. This is same as V actual. So I can write down this in the following fashion: V actual is equal to C transpose Z primitive C into I actual. Ultimately I have to get the equation in the actual variables. So the impedance matrix Z primitive can be transformed with C transpose multiplied, pre-multiplied, and C post multiplied. So this is my Z actual. So this is the advantage of linear transformation. It means using the linear transformation I can get back the impedance matrix in the actual variable, in the actual machine. Okay. So for this equation, what is the Z primitive here? So we can say that V actual in this case is Vt, and C transpose is 1 1, and Z primitive is given by Rf LFP 0 MD omega R RA LAP, and it is post multiplied by C, and I actual is IT. Now in this case, if you go back to the previous slide, you will see here that in the stator we can say that IDS RDS equal to RF. This is the field winding. All right. LDS is equal to LF. The field inductance is same as the LDS, and similarly RQR is equal to RA, the armature resistance, and LQR is equal to LA, is the armature inductance. So these are the various values of the parameters of the machine. Now we can replace this RDS by RF, LDS by LF, RQR by RA, LQR by LA. So this equation is the equation of the DC series motor in actual variables. Now we can simplify this because this is a matrix equation. So if we simplify this, we can pre-multiply and see what happens here. So, it is RF plus LFP plus MD omega R, and then here RA plus LAP and then we can post multiply this and see RF plus LFP plus MD omega R plus RA plus LAP. So, we can also simplify this. We will have RF plus RA into IA plus MD omega R IT plus LF plus LA into P of IT. So, this equation that is equal to Vt is the equation of a DC series motor. We have seen that in the series motor the field and the armature are in series. So, the resistive drop is Ra plus Ra, and then the inductances are also in series. So, the self inductance is LF for the field winding, the self inductance is LA for the armature winding. So, it is LF plus LA into P of IT, IT is the current, and the rotationally induced EMF is MD omega R IT, that is also appearing in this equation. Okay. Now, we can directly find out the torque equation taking the help of the primitive equation. So, let us see how we can find out the torque. Now, we know that the torque is given by P by 2 I transpose G I. Now, these are the primitive current, I can say primitive. So, I know that the primitive current I primitive is equal to C into I actual. This we know this. So, I can replace this primitive by C I actual. So, that will be C transpose I actual G C, this is I actual C transpose G C I actual, all right, and I actual is IT, this is C transpose G C I T, and I can write down what is this G matrix. C transpose is 1 1 and the G matrix is 0 0 MD and 0. So, further simplification will lead to IT square, IT is here and IT is also here. So, then I have MD and 0 and post multiplied by 1 and 1, and then what I finally obtain is P by 2 IT square MD. So, this is basically the expression for the torque of a DC series motor. So, this we have obtained from the Kron primitive machine model using the principle of linear transformation in electric machines. Now, let us take a different problem. We will take a separately excited DC machine, but in this case the brass is little shifted from the magnetic neutral axis. Okay. So, what we have here is this, that we have a DC machine here, This is the field winding. We apply the voltage Vf here. This current is If, the field current, but the brushes are not in the magnetic neutral axis. That is not in the Q axis. This is the D axis, and this is the Q axis. The brushes are shifted and they are placed in this direction, and this angle is alpha. So, this is the situation that we have. I mean, we have little different type of DC machine here, where the brass axis is shifted from the magnetic neutral position. Okay, this may be true when we have the shifting of the brass from the magnetic neutral position. We will have the situation like this, and this is the armature, and armature is applied with a voltage. So, this voltage is VA, all right, and this is passing a current here, that is IA. Okay, and we have a pseudo stationary winding, as we already seen, that the armature can be replaced by a pseudo stationary winding. The commutator and the brushes can be replaced by a pseudo stationary winding. The axis of the pseudo stationary winding is the brass axis. So, this is a pseudo stationary winding, and what we can do here, we can have a component of the winding. We can have a D axis rotor and a Q axis rotor, and this is dr, and this one would be qr. So, if the original armature winding was in A, this winding will also have the number of turn that is equal to Na. The Q axis winding will also have the number of turn that is equal to Na. So, what we want to do here is the following, that since we have the armature winding in some arbitrary axis inclined with the D axis at an angle alpha, we can simulate that by having a D axis rotor winding, that is Dr, and Q axis rotor winding, that is Qr, and the number of turns of this Dr and Qr will be the same as that of the original armature winding, that is Na. So, the number of turns of these windings are same as the armature winding number of turns, that is Na. And we can say that IDR, if you equate the MMF in this case, we can say IDR is equal to IA cos alpha. Very naturally, we can say that this is the projection of this along the D axis. So, this is IA cos alpha, and IQR is equal to IA sin alpha. All right. So, we can, we are talking about the shifting of the brass axis, and IDR equal to IA cos alpha and IQR equal to IA sin alpha, and this is the D axis stator winding DS. So, we can also say that IDS is equal to IF. So, we are relating the primitive variables with the actual variables. Actual variables are here the armature current and the field current, and the primitive variables are IDR, IQR and IDS. So, we can write down the connecting matrix in the following way. So, the connecting matrix is C, and we can say that IDS, IDR and IQR, that is equal to this is our IF, the field current and the armature current, and this matrix is 1 0 because IDS equal to IF, and then IDR equal to IA cos alpha. So, this is 0 cos alpha, and IQR equal to IA sin alpha. So, this is 0 and sin alpha, or we can say that it means we can write here that I primitive is equal to C, the connecting matrix C into I actual. So, this is your I actual and this is the I primitive. So, this C has been determined. C is equal to 1 0, 0 cos alpha and 0 sin alpha. So, in a similar way we can write down the expression for the voltage. So, the voltage and currents are related. So, we can write down in this case VDS and VDR and VQR are the voltages of the primitive variables in terms of the actual variable voltage, that is the VF and VA. Now, what is VF? VF is the field voltage here, and VA is the armature voltage, that is the VA applied here. So, we can rewrite like this, and VDS equal to VF. We can see here that VDS and VF are the same. This is VDS, and this terminal is a positive terminal closer to the center as per the convention. So, VF is equal to VDS. And what about VDR? VDR would be VA cos alpha, just like the current. Since the current is multiplied by cos alpha, voltage will also be multiplied by cos alpha, because only when the voltage is reduced, current is also reduced. Similarly, we can say that VQR is equal to VA into sin of alpha. So, we will have here that 1 and 0, VDS equal to VF, and VDR is VA cos alpha, VQR is VA sin alpha. So, this is our matrix which relates the primitive variables. This is V primitive is here, and this is the V actual. All right. So, we will pre-multiply with C transpose. This is our C. Now, if you pre-multiply with C transpose V primitive. Now, if you see C transpose into C here, that will be I matrix. So, we can say that C transpose V primitive is V actual. So, if you pre-multiply this with C transpose, in this case C transpose into C is a identity matrix that can be verified here. So, we can say here that C transpose into V primitive is equal to V actual. So, this is what we have for this situation. Now, if you see that the primitive equations are as follows, we have 3 windings here, and the windings are DS, DR and QR, and similarly we will have 3 different currents, and the currents will be IDS, IDR and IQR. So, we have to fill up this 3 by 3 matrix. You can see here that we have 3 windings, that is DS, DR and QR, and correspondingly we have VDS, VDR and VQR, IDS, IDR and IQR. So, that is what we have written here, and this would be the resistive drop plus LDSP. We can fill up this matrix by inspection. We do not have to remember this. The stator does not have any rotationally induced EMF. The rotor will have the rotationally induced EMF, because this is rotating in the clockwise direction at a speed of omega r. The rotor is in rotation. So, there is a mutual coupling between the d axis rotor and the d axis stator, that is MdP and 0. Similarly, for the second row we have RDR, LDRP. Now this is MdP, and we have the rotational induced EMF, that is omega R LQR. The third row would be RQR plus LQRP, and then we do not have any coupling with the d axis stator, but there will be rotational induced EMF. So we have omega R into MD, and here we have omega R into LDR. So this is your V primitive, and this is I primitive, and this is the Z primitive. Now we want to have the equation in the actual variable, so we have to use the transformation here. So using the transformation, we can transform this primitive equation into the equations of the actual variables. So we have here that I primitive is equal to C into I actual, and C transpose V primitive is equal to V actual. And we also have V primitive is equal to Z primitive into I primitive. This we have already derived. V primitive is equal to Z primitive into I primitive. And here if you pre-multiply this with C transpose, C transpose V primitive is equal to C transpose Z primitive. We can replace I primitive by C into I actual. So this equation will give us the equation with actual variables, because C transpose V primitive is V actual. V actual is equal to Z actual into I actual. So Z actual in this case is C transpose Z primitive into C. So we can evaluate what is Z actual. So Z actual is given as C transpose Z primitive into C, and that is equal to C transpose is 1 0 0 0 cos alpha sin alpha, and then Z primitive is RDS plus LDSP MDP and 0, MDP RDR plus LDRP minus omega R LQR, omega R MD, omega R LDR, RQR plus LQRP. And then we can post multiply with C, that is 1 0 0 cos alpha 0 sin alpha. So this is what is Z actual. So we can simplify this. I will just write down the simplified equation. We can pre-multiply this and post-multiply this and write down the simplified equation. So let me just write down the simplified equation of Z actual. Z actual after simplifying is obtained in the following fashion. It is RDS plus LDSP MD cos alpha P. P is the derivative operator, d by dt, small p is d by dt, and MD cos alpha P plus MD sin alpha into omega R. Then here we have RDR plus LDRP cos square alpha plus omega r LDR sin alpha cos alpha minus omega r LQR cos alpha sin alpha plus RQR plus LQRP into sin square alpha. So this is Z actual. Now we can replace RDS by RF, the field resistance. RDS is the field winding resistance. The D axis stator is basically the field winding. So RDS is equal to RF and LDS is equal to LF. RDR equal to RQR, that's equal to RA. The two windings in the D axis and Q axis rotor has same number of turns. Each one is having the same number of turns, and that is the resistance of the armature, that's equal to RA. And then LDR is equal to LAD, the armature inductance in the D axis, and LQR is equal to LAQ, the armature inductance in the Q axis. So when we substitute this RDS, RDR, RQR, LDS, LDR, LQR in the equation for the Z actual, what we obtain is the following. So we can say that Z actual after simplifying will be of this sort: RF plus LFP. Now this is MD cos alpha P, and here we have MD cos alpha P plus MD sin alpha omega R, RA plus LAD cos square alpha plus LAQ sin square alpha P plus LDR minus LQR by 2 into omega R sin of 2 alpha. So this is the equation of the Z actual. It means the actual impedance matrix of this machine has been found out by using the linear transformation. Okay. So the last thing what remains here is that we have been able to find out the voltage equation, because once we know Z actual, we can write down V actual is Z actual into I actual. The voltage equation has been written. We have to find out the torque equation. Now the torque equation can also be found out from the Cron primitive machine equation. We know that TE is equal to P by 2 I transpose G I. So this we have seen from the Cron primitive machine equation. Now this I is I primitive, and here is I is I primitive. So again we replace I primitive by C into I actual. So that's what, if you do, what we have here is I actual transpose into C transpose G C I actual. Now that's equal to P by 2. What is I actual? I actual is IF IA, and the transpose of I actual is a column will be a row matrix, that will be IF IA, a row matrix. What is C transpose? C transpose is given by 1 0 0 0 cos alpha sin alpha, and the G matrix is the matrix associated with the speed term. Okay. So we can find out this G matrix from the primitive machine equation, that is 0 0 and 0 0 0 minus LAQ MD LAD 0, and then we will post multiply with C. The C is 1 0 0 cos alpha 0 sin alpha, and then we have I actual is IF IA. So, this if we simplify this equation, we will get the equation for the torque in the actual variable, because actual variables are IF and IA, the field current and the armature current respectively. So, we can simplify this. So, if we pre-multiply this, what we have here is IF IA, and this would be 0 0 and 0 MD sin alpha and LAD sin alpha, and then minus LAQ cos alpha. So, this is basically a 2 by 3 matrix, 2 rows and 3 columns, and then we post multiply this with C. C is 1 0 0 cos alpha 0 sin alpha, and then we have the current, that is IF IA. We can further simplify this and get the final equation. So, further simplification will give us P by 2. We can post multiply this, and then we can pre multiply with IA into IF. So, what we obtain here is that MD sin alpha IA LAD minus LAQ by 2 into sin of 2 alpha into IA, and post multiply with IF and IA. Okay. Now, further if you simplify this, we get P by 2 MD sin alpha IA IF plus LAD minus LAQ by 2 into sin 2 alpha IA square. Now, this equation is an interesting equation in the sense that there are two components of the torque. One component is coming because of the first term. Now, this is IF into IA. This is something like a normal torque of a DC machine, the product of IA and IF. But the second component is basically proportional to IA square. All right. So, this is not the convention. I mean, in case of a DC machine, the torque is produced by interaction of field current with armature current. But the second term shows that this torque is proportional to IA square. All right. So, you can see here that if you take the original machine in this case, that alpha for a normal machine, alpha is pi by 2, alpha is 90. Now, if you substitute alpha is 90 in this equation, you will see that sin of 90 is 1. So, this is MD into IA into IF, which was the equation for a separately excited DC machine. And here if you put alpha is 90, it will be sin of 180, that is equal to 0. So, this torque will be 0 if alpha is 90. So, this is actually for this lecture. So, in this lecture what we have studied is the following. To summarize, we have seen how the generalized theory of electric machine can be used to simulate a DC machine. We have taken the example of DC separately excited machine, DC series motor, and also a DC machine where the brush is shifted from the magnetic neutral axis. And we have seen the equation for the torque. We have also seen how linear transformation in electric machine will be helpful in transforming the variables from the Cron primitive machine model to the actual machine model. So, this is a linear transformation because this transformation does not involve any product of variables or any higher square or cube of the variables. So, in the next lecture, we will be discussing the modeling of induction machine, which is a 3-phase machine, which is a AC machine, which is more complex than a DC machine, and we will see how the generalized theory of electric machine can be applied to simplify the model of a 3-phase induction machine.